me know. All right, so this is Math313, lecture 24, and then hopefully it will track over here. Okay, good. All right, so what I want to do today is I want to talk a little bit about the p-adics and Hensel's lemma. But this is also a special day. This is Patriots Day in Boston. And so this is the day of the Boston Marathon. Normally I give a lecture on the Pythagorean one-loss theorem. And I do a sabermetrics baseball lecture. I'm not going to do a full sabermetrics lecture today, partly because a lot of you have already seen me give it. But what I will do is I will do a small subset. And I will do the subset that I normally don't include when I give that lecture. And so what I want to do is I want to display four possible formulas on the board. P plus PQ over P plus Q plus PQ, P plus PQ over P plus Q, I wanted a 2 here, minus 2PQ, P minus PQ over P plus Q plus 2PQ, and P minus PQ over P plus Q minus 2PQ. Okay, so there are four formulas on the board. And so imagine A wins P% of their games, and B wins Q% of their games. And they've never played each other. And we'll assume they've played similar teams. And we want to predict what is the probability that A beats B. So there's four candidates on the board. The reason I want to do this is, one, it's related to baseball, and this is a good baseball day in Boston. You know, game starts at 11. And two, as you go further and further in math and science, you start to see more involved formulas. So one of the most important things is to look at a formula and get some sense of what it's saying, what should be reasonable. So these formulas are all very similar. Where's the only places where they're differing? So where are the places where they differ? Pluses and minuses. So the top over here is either a plus or a minus, and this is why I want to write them in the same way. And then the bottom over here is either a plus or a minus. So it's minuses over here and plus minus over here. Okay? So there's four possibilities because I have two choices for sign. Okay? So there's two choices of sign for the top. There's two choices for the sign on the bottom. There's four possibilities. One of them is a pretty good estimate of the probability that team A beats team B. The other three, oh, I've got to be careful, my kids are here, is less good. Okay? 4-letter word starts with S. Or maybe 5-letter words with 2 S's at the start and the end. Okay? How would you figure out which one of these is a good predictor? Or conversely, how would you figure out which one of these is bad? How would you analyze something like this? How would you think about something like this? Yes?
You can just assign values.
So you could assign values. Any thoughts of a good value to assign to either P or Q?
Assign one to be 1 and the other to be 0.
So assign one of them to be 1. You know, this is the invincible team. And assign one to be 0, the team that always loses. So if we do, let's say P equals 1 and Q equals 0. So if P equals 1, this is 1 plus 0 or 1 minus 0. So the numerators are always 1. And then down below, the denominators are always P. So if we try, is it in focus if I write over here? If I try P equals 1 and Q equals 0, there's no info. Unfortunately, all of them collapse to giving 1. It's a great thing to try, but it's not useful. Yes?
Maybe try P is 1, but Q isn't 0?
Okay, so we could try P is 1 and Q is not 0.
Or 1, because two invincible teams playing each other would be kind of weird.
Well, so if we have two invincible teams playing each other, it would be fascinating as to what do you think should happen. When I was young, my brother and one of his good friends were playing an old baseball game where you could create your own characters. And they created the pitcher who always strikes out every batter and the batter who always hits home runs. And the two fought each other. And the computer hung up for several minutes. And we thought, oh my God, did they crash the computer? Eventually, the computer outputted the only possible result for the pitcher who always strikes out everybody and the batter who always hits home runs.
Can we do 1 off for both?
Well, first of all, what do you think it would be in that case? A double. So after a long time, the computer said, batter always gets 4 bases, pitcher always gives 0 bases, on average 2 bases. So what would be another thing? So one thing we could try is if Q is a little bit greater than 0, what would happen? What do you think the answer should still be?
Should still be 1.
So do you think it should still be 1?
Well, because P always wins, and Q wins some percentage of games. But I think it should be slightly less than 1.
So it should be slightly less than 1.
It's like the probability that A wins, or this is like A's win percentage.
This is the probability that A beats B. So whenever you have something that's perfect, it could be a little...
Is P percentage the number of games they've won?
Yes, P is the percentage of times A has won, Q is the percentage of times B has won. So, one possibility is I could try Q as maybe a small number, maybe Q is epsilon, and I could try going through that. But there are other cases that are much easier to look at than this. So I'm not saying that this is a bad choice, I'm saying there's better choices than 1 and epsilon. I'm sorry? Could we do what?
1/2.
Oh, 1/2, yes. So try P equals Q equals 1/2. You have 2 average teams play each other. What should the probability of A beating B be? 0.5. So if we try 1/2 for both, we can go look at what would happen in these cases. So in this case, we would have 1/2 plus 1/4, which is, so we'd have 3/4 divided by 1, and then we would have another half, so that'd be 3 halves. What's 3/4 divided by 3 halves? 1/2. So this is still alive. Right? What about this one? That would be less than 1/2. So we can eliminate this one. Right? So we know that this one can't be it just by looking at the possibility of 1/2, 1/2. What if we try this one? We would have 3/4 over something, so we can also eliminate this one. And if we do this, we would get 1/2 minus 1/4 is 1/4. And down here we would have 1 minus 1/2, which is 1/2. So this one would also be alive. So just looking at the 1/2, 1/2 case, we've been able to eliminate 2 out of the 4 candidates. What else could we try? What would be another good thing to look at? So again, it's trying to look at special cases. This is one of the things we've talked about in this class. When I give you something, do special cases, investigate low values first, see what goes on, build your intuition, and then try to push it forward. So one thing we could try, the 2 invincible teams. Yes?
So, just for clarification, so those percentages are not like head-to-head necessarily?
No. So we'll assume A and B have never played each other, and we're trying to estimate what do we think the chances that A would beat B if A wins P% of their games and B wins Q%. So if 2 invincible teams play each other, what do you think the probability that A wins should be?
50%?
Probably 50%. So if we tried 2 invincible teams, this would give us 1 plus 1 is 2 over 4, which would be 1/2. And this would give us 0 over 0. Oh, 0 over 0 is undefined. And maybe that is the same thing as the 1/2. So unfortunately, if we try the 2 invincible teams against each other, it's not going to work.
Yeah, but that would be crazy. That 2 invincible teams just I'd be mad.
Well, if you have 2 teams that have never lost that play each other, one of them has to lose. One of them wins. So if I had to guess, I would expect 1/2 would be the reasonable thing. And this could be 1/2 because I've got 0 over 0.
Did the game just not go forever?
Well, we're imagining a situation where A and B haven't played each other yet, and we're trying to estimate what do we think the chance that A would beat B. So imagine we have 2 sports leagues where you don't meet each other until the championship. And so now they have a lot of interconference games, so you often do have some data points. What if you have P is greater than 1/2 and Q equals 1/2? What do you think the probability that A should win would be?
More than half?
More than 1/2. How much more?
Well,
It's going to be around 0.7.
wouldn't it be basically just whatever P is?
So would it be P?
I mean,
Maybe because now we're playing an average team. If we put in 1/2, we have P plus 1/2 P.
The average should be like slightly less than 1/2 if you discount P, but I guess, yeah.
Well, so let's put in P equals 1/2. So in this case, we would get 3/2 P, right?
Yeah.
So here we would have 3/2 P, and what would we get down below? We would have, so 2 times Q would be 1. So we would have 2P plus 1/2. Does that look reasonable? Let's see what we would have down here. Here we would have 1/2 P. And down below, this would be P minus P. And we would just have 1/2. So this formula down here will actually give us P. Over here, all you would need to do is try to look at this and see, is there a choice of P where this doesn't seem to make sense? If I take P equals 3/4, if I take P equals 3/4, I'm going to erase this now because we know this is wrong, and I'll erase this one here because we know this is wrong. So if I take P equals 3/4, that would give us 9/8 divided by, 3/4 times 2 is 3/2 plus 1/2 is 2, right? So this would give us 9/16. Does 9/16 seem reasonable? So A's winning percentage was 3/4. How many 16ths is 3/4? 12. So against an average team, A is winning 3 out of 4, winning 12 out of 16. They now play an average team, and the formula is telling us 9/16. Does that seem reasonable? I would say it fails the test here. You would expect if I'm playing an average team, I should just get back P. So the only formula that's surviving is this one over here. The other thing is, what if I chose P was greater than 1/2 and I chose Q was less than 1/2? What should be true about the probability of winning in this case? It should be more than P. So this is another test you could do and look at these formulas. And when the dust settles, the only one of these 4 formulas that works is the last. Okay? And I want to leave this on the board because there's a nice way of looking at this. So much of mathematics is about how you view things. So again, most of you are not going to use number theory, but you might actually look at the sports page at times. So I don't feel too bad spending some of today talking about this. How should we look at the numerator?
P times 1 minus Q.
Yeah, let's look at P times 1 minus Q. Can you give me an interpretation of the numerator?
A wins and
Probability P wins and Q loses.
Probability that A wins and B loses. Or maybe another way of looking at it is the probability that A plays well and B plays poorly. How should we view the denominator? So again, so much of life is dealing with algebra. Any thoughts? Yes?
It's the probability that A plays well and B plays poorly plus the probability that B plays well and A plays poorly.
Yeah. What we can do is we can rewrite the denominator as P minus PQ plus Q minus PQ. Is write the denominator like that. And now we get P 1 minus Q plus Q 1 minus P. Or maybe I should write 1 minus PQ like this to keep the order the same. This is the same expression as this over here. This is just P minus PQ over P plus Q minus 2PQ. But when you look at this, it makes a lot more sense as to where it's coming from. This is called the log 5 method. I can explain roughly why it works. I cannot explain the name. Some of the names in sabermetrics are quite strange. So let's imagine team A and B are playing. And if A plays well and B plays poorly, A wins. If A plays poorly and B wins, B wins. What happens if they both play poorly?
Better team wins.
Well, they both play poorly.
Well, the one that played, I think we're defining like playing poorly by like losing and playing well.
All right, so let's do it this way. Let's say a head always beats a tail. And P is the probability that A gets ahead. Q is the probability that B gets ahead. And if you get ahead and the other person gets a tail, you win. If you both get heads, what happens? You play the game again, extra innings. If you both get tails, what do? Yeah, so let's look at what happens. So we can have a decision tree. A does well, A does poorly. And the probability that we come here is P. The probability we come here is 1 minus P. And then over here we could do B well, and we could do B poor. B well, and B poor. And this probability would be Q, 1 minus Q, Q, 1 minus Q. So now to come down here, the probability we end up in this point is PQ. The probability we end up here is P, 1 minus Q. The probability here is 1 minus PQ. And the probability here is 1 minus P. Guys, you got to, Cam Kelly, you got to be quiet. Okay? So the probability we end up here is 1 minus P, 1 minus Q. What happens if we're in this situation? Play again. What happens if we're in this situation? You play again. So if you want to look at this in terms of probability, these two opportunities terminate, and otherwise we reset the game. So it's a conditional probability. So the probability A wins is here, and I have to divide by the probability I'm in one of these two places. Another way, if you want, is you can imagine you do 1,000 games, and you can see how many of the games end up in these two states and take the fraction. And so this is where the numerator comes from, and that's where the denominator comes from. Okay? So the whole point of this was to just talk a little bit about how to analyze equations, how to do special cases, and take the knowledge from those special cases and push it forward. Okay? So again, you're going to get more and more involved equations as you go further and further. If you can get into places where you can get a sense of what's going on, that's a huge advantage. Okay, what I want to do now is I want to shift a little bit and motivate Hensel's lemma. Now, I think about half of you have done differential equations. So, one of the things you always want to know when you're doing something in mathematics is, when is it useful, or when is it just like a one-time wonder? Yeah. The idea of Hensel's lemma, of taking a solution and building it up and making it larger and larger and larger, you're adding higher and higher powers of primes. This is a great idea. So let's try to solve the equation y double prime of x is negative y of x. All right. Does anybody know something that would solve this? Yes?
Sine of x.
Sine of x. Anything else? Anything else? Negative sine of x. Anything else? Ah, so basically linear combinations of sine and cosine should work. Okay? So what we can do is we can guess y of x is the sum of an x to the n, and goes from 0 to infinity. And if we just take two derivatives and we assume we can switch the order of the derivative and the sum, what would we get? We would get n minus 1, an x to the n minus 2. This should remind you of the generating functions we did earlier in the semester with the Fibonacci's. What don't we like about this?
Well, it goes below 0.
It goes below 0, so where should the sum really start? The sum should really start at 2. And if you think about it, we have an n and n minus 1. So when I take two derivatives, the constant and the linear terms, they vanish. So it's really a sum from 2 to infinity. And now what we do is we play the index game. So we want to rewrite this. We would love this index to go 0, 1, 2, well, it does go 0, 1, 2, 3. We've just labeled it. So what I want to do is I just want to change things. So let's say m goes from 0 to infinity. We'll have x to the m. So m is n minus 2. So what should the subscript of a be? I'm sorry? M plus 2. If m is n minus 2, then n is m plus 2. Right? And now n becomes m plus 2. And then the next is m plus 1. So we get m plus 2, m plus 1, a m plus 2, x to the m. Do I have to use the letter n? Do I have to use, I can use any letter I want. I found over the years it's easier for students to use a different letter here than to immediately write n. But this would be the same as the sum, n goes from 0 to infinity, of n plus 2, n plus 1, a n plus 2, xn. It doesn't matter what letter I use. And now I want this to be the negative of this. Okay, so let's see. Okay, hope am I somewhat in focus? So we're solving y double prime of x equals negative y of x. Okay, Cameron and Kayla, if I hear you one more time, I'm taking it away. So we have y double prime equals minus y. So what do we get? We get a sum, n goes from 0 to infinity. Y double prime will be n plus 2, n plus 1, a n plus 2, minus, well, when I subtract the y, I bring it over, and it becomes a plus, right? Plus an a n x to the n equals 0. So this is what I get when I add y of x to both sides and set it equal to 0. What is the only way that infinite sum should be 0? Yes?
If all the components are 0?
All the components need to be 0. So we need a n plus 2 should be negative a n over, oh, this should be n plus 1, sorry, over n plus 2, n plus 1. So we have a recursion for the a's. Each a is specified once you know 2 earlier. And you might begin to see where the sines and cosines are going to come from. So let's start off with a0. Do we know any information about a1 once I tell you a0? No, a0 gives us no information. We only have information 2 down the road. Okay? All right, let's look at a2. What's the relationship between a2 and a0? So it'll be negative a0 over 2 factorial. So you get negative a0 over 2 factorial. What about a3? Well, a3, I have a 1 here, so it'll be negative a1 over 3 times 2. What's 3 times 2? Turns out it's 3 factorial. So I'll get negative a1 over 3 factorial. Now let's look at a4. a4 is going to be negative a2 over 4 times 3. And I've got an a2 is negative a0 over 2 factorial. So when the dust settles, I get a0 over 4 factorial. What do you think I'm going to get down here? a1 over 5 factorial. And then here I'll get a negative a0 over 6 factorial. Here I'll get an a1 over 7 factorial, dot, 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 dot. This is going to give me a0 cosine x. And this will give me a1 sine of x. And this is, for differential equations, I have a second order differential equation. I have 2 derivatives. That gives me 2 free parameters, the a0 and a1. And you can see how we can piece the information together. This is the same local to global. We're solving these local problems and we're building it up and we're getting a global solution. This is the whole idea of the p-adics. This is the whole idea of Hensel's lemma. We want to solve, we want to try to find a solution modulo a prime, modulo powers of that prime, and then we want to somehow lift that to a general solution. What's nice is if you're solving things modulo a prime, let's say you want to solve things modulo 17, how many things do we have to check? To try to solve something, an equation in x modulo 17, how many candidates are there? 17. That's not that bad. That's a finite problem. What if we want to look at something modulo 17 squared? Whatever number 17 squared is, that's how many things to check. Okay? What about 17 cubed? Whatever that is. It's a finite problem. And the idea is if we can solve each one of these finite problems, we can piece it together. Okay. So I want to show one last thing about primes, and then I want to shift to Hensel's lemma. Okay, so Kayla, this is the part you haven't seen, and I need you to now pay attention. Okay, do you want to come up here and help? Okay. So you had asked earlier, Kayla, what Pascal's triangle is. So I'm going to show you this, and then we're going to watch the movie. Okay, so the movie was written many years ago, because I couldn't find it on the web, so I had to make my own. Pascal's triangle. And Kayla, you're on. This is for an extra dessert. Are you ready? The left and the right are always ones. Okay? And then anything else is the sum of the number immediately left and immediately right above it. So the next row is 1, 1. I start and end with a 1. This number is the sum of the numbers right above it. So what would I get? 2. What do I start the next row with? What do I start the next row with? What do I end with? What goes here? Which is? What goes here? So I got this 2 by summing the two numbers, the one to the left and one to the right. So what would I get over here? And what would I get over here? All right, what's the next row? Start and end with a 1. So now what do I get here? What comes after 4? Which 6. I will do one more row. What do I start with? Okay, 1. Okay, and so the pattern continues. So hopefully everybody here has seen Pascal's triangle. I'm sorry? You can get another dessert as long as you keep behaving, yes. All right, so have we all seen Pascal's triangle? As long as you keep behaving, yes. Okay, and for the students, as long as you keep behaving, you can also have an extra dessert. Yes? Okay, don't tell your parents. Although this is being recorded. So of course have vegetables first. So everyone has seen Pascal's triangle. How many have seen colored Pascal's triangle? Okay, so what we're going to do is if it's an odd number, we're going to either color it or make it a dot, and if it's an even number, we're going to erase it. And the question is, what happens as we draw more and more rows? What kind of structure emerges? Now, when you think about, even is remove, odd is you color. What should you be thinking about? What are we really doing to Pascal's triangle? Not quite binary, close. We're looking at it mod 2. This is supposed to be a warm-up to Hensel's lemma. This is supposed to be a warm-up to the p-adics. We're looking at Pascal's triangle mod 2. How many of you have ever looked at Pascal's triangle mod 2? If you've taken a probability with me, your hand should be up now, okay? I'm pretty sure we did this in probability, okay? Could you look at Pascal's triangle mod 3? Sure. Mod 4? Yeah. You can do mod anything you want. And the question is, what kind of structure emerges? So I couldn't find this on the web, so I wrote a Mathematica program to do this. To make things a little bit easier, when I'm printing it out, I'm fixing the size of the computer screen to always be this. and I'm rotating my triangle so that my point, my vertex, is in the middle over here, and it goes like this, okay? And if I have 10 rows, I rescale it so that the 10th row is here. If I have 100 rows, I rescale it so that the 100th row is here. The reason is I cannot have the blackboard screen increasing as I run further and further down. So I always want to keep adjusting the size. Okay, if you've never seen this before, it's a nice thing. It gives a nice illustration of what's going on. Okay. Okay. All right, hopefully it's going to be somewhat in focus. All right, so can everybody see the 3 dots? I've done 2 rows of Pascal's triangle. You know, this is 1, 1, 1. The next row is 1, 2, 1. So it should be dot, no dot, dot. And I'm going to play it at a somewhat slow speed. Okay, Caleb, watch this. So this is Pascal's triangle where you put a dot if it's odd and you remove it if it's even. Yeah, I thought I had shown you this movie. Okay. So for those of you who've taken probability with me, you're not allowed to answer right now. For those of you who haven't seen this before, what do you see? You see a fractal. Yes, Kayla. You see triangles, triangles and triangles and triangles and triangles.
Many triangles in one triangle.
Yes.
And the dots are forming the triangle.
And the dots are forming the triangle. And this pattern over here is then repeated here and here. And then this whole thing here is going to be repeated down here and here. And then these whole things here will be repeated and repeated.
Why does it stop?
It doesn't. It goes on and on forever. And so it's an interesting question as to how do you write this program to display it quickly and efficiently. So I'll speed it up a little bit.
Is it equilateral?
Is it what?
Equilateral?
It's not quite equilateral just because of the aspect ratios. But you can choose to have it equilateral. You can choose to have it a right triangle. You know, it doesn't really matter how you do. We're reaching the point very quickly where the resolution of the dots is getting to the point where I'm not really able to see, I think, too much additional detail.
The dots
Is it going to be
are
full
forming
at some
together.
point?
Is it going to be, what do you mean by full?
Well,
Well, so if you want to ask questions about what is the dimension of this object, the dimension of this object is greater than 1 and less than 2. So it has a fractal dimension. If people are interested, we can do stuff related to this. We can do the standard Cantor set, which you see in real analysis. You're about to lose dessert, kids. We can do things related to the Cantor set, which is related to base 3 expansions of numbers. And so this is all connected to different types of expansions for numbers. At this point, the dots are now so close to each other because of the size, I can no longer really see the additional structure. So I'm going to just pause it here.
does it go forever?
It goes forever. You just keep getting more and more rows, and it keeps repeating and repeating. This whole block here is then going to come in here and here, and then these whole things will keep going and going and going.
When does the computer write?
I think I've done it to maybe around the order of maybe 2,000 or 8,000, maybe 8,000. No, I guess around 2,000. And so beyond that, I'm not doing the best job in terms of how I'm calling the results, because I am not an expert programmer. So I'm doing some kludges to program it. Now, what I could do in some sense is the resolution is not sufficiently sharp, so beyond a certain point, I can actually cheat and not really display it properly because you won't be able to tell the difference. They do this sometimes for recordings because you're not going to be able to tell the difference. They can round a few things. Related to this, actually, is encrypting information. And so I will, maybe I'll show that. Cam, can you hit the mute button? Or Kayla, can somebody hit the mute button on the computer?
On my iPhone?
No, on the big program over there. Okay, so let me see if I can quickly push this up.
I think they're dark.
Because I've got things, so this is a nice way to okay. Okay, here we go. So just as long as we're doing this, keyboard on this computer is old and crappy. Okay, here we go. Okay, can you unmute it? It's the one that's flashing red. This is one of the few times it's okay to hit something that's blinking red. It's not dangerous. All right. One of the whole points is to show you applications of number theory, applications of things we've done. If any of you are terrorists, please let me know after class so that you don't use this to attack us. This is a nice picture of a tree. All right, this is a picture of a tree. My son looks at this and sees a cat.
I see trees.
You see trees? Wait.
Cats.
Oh, I do see a cat. Does anybody see the cat hidden in the tree?
Yes.
I know where the cat is.
Okay, so, yeah. Does anybody see the cat?
Well, I mean, I just know where I don't see it, but I know where it is.
Yes.
So that's why I
Does anybody see the cat?
Yeah.
You want to see the cat in the tree? You want me to show you?
I see it.
Really have no choice. So, good resolution picture of the cat or bad resolution picture? Not very good. Good picture or bad picture of the tree?
Not very good.
Better or worse than the cat?
But
I think better. It's not the crispest image possible, but it's not a bad image. So I'm going to show you how to use base expansions to hide cats in trees. And you can use this to have secret messages. Okay? Okay. So when you have an image is a bunch of pixels. And so, maybe we have an n by n, and each one of these pixels gets a different color. Does anybody know how we assign colors to pixels? There's a bunch of ways.
But in general, not like red and green
Yeah.
and blue.
You give a triple, the red, green, blue triple. Okay? Normally, we often assign these numbers from 0 to 255.
And then you choose the frequency that you want. Gives you like mix of colors.
Right, so you would say how much red, how much green, how much blue. Okay? When you see the number 255, or 0 to 255, what should you be immediately thinking about? Yeah. Binary. This is 1 less than 256, and I'm starting at 0. So my binary, 1, 2, 4, 8, 16, 32, 64, 128. A0, or maybe we'll do R0, R1, R2, R3, R4, R5, R6, R7, and our red will be just the sum. K goes from 0 to 7 of RK 2 to the K. And that will give us our red value. And we do something similar for the green, and we do something similar for the blue. And we then transmit the red, green, blue. Now, if you wanted to transmit every pixel of every image, this is going to be expensive. This is a lot of information to transmit. What we can often do is we can take these RGBs, and things should probably vary for the most part continuously, except when you get maybe sharp breaks between regions. And what we can do is we can transmit the change in these from frame to frame. And then what we can do is we can actually use Fourier analysis to transmit the change very quickly. So I'll be teaching a class on advanced analysis next year. One of the things we will be doing is Fourier analysis and how you can very quickly send information. What you can think about this is, if I give you the red function on this whole square, if I do a Taylor series, the hope is that a Taylor series, a few terms, does a really good job of explaining what the function is doing. And then rather than transmitting every single pixel color red, I just have to transmit a few pieces of information, and then I can build the red function to a close enough approximation that your eyes can't tell the difference. And this is where Taylor series come into play, but there are things that work better than Taylor series. There's Fourier analysis and Fourier series. There's wavelets. And so this is something that we will cover in Math 466 next year. But it's coming from a base expansion. We're expanding things in base 2. Imagine I refuse to let you use the last 2 digits, or maybe the last 3 digits. I know. I'm sorry. Kayla? Alex is sad. Do you want to give him a hug or no? No? We're in about 5 minutes. Okay, in 5 minutes. So imagine I don't let you use R0 and R1. How big of a deal is that going to be when you're choosing your red, green, blue values? Not too much. How much can we move from where we want it to be by not having access to those two? I'm sorry?
3. Like, we can only be like 3 off 4.
Yeah, and in fact, so we lose the ability to choose, 0, 1, 2, 3. We're always being a 0. Right? If we wanted to, we could maybe even choose something halfway in between or something like that to try to maybe minimize the amount we're off by. The idea is you take your image and you remove the last 2 digits and you use that to encode the other image as low resolution. So for the cat image, we would just color the cat just using 2 things from 0 to 4, or maybe 3 things, 1, 2, and 4, so we could get from 0 to 8. If you do that, is the cat image going to be sharp? No, of course not. But the odds that you'd be able to detect this in the main image is really small. So the question is, can you determine if somebody has actually modified an image? And so there's a lot of tests to do. This is another thing we will talk about in Math 466 next year. We'll talk about Benford's law of digit bias. I remember years ago I was watching a Red Sox game on the nightly news the next day, and there was a little bit of a scandal. Because what happened is the game was on one network, and it was being rebroadcast on the nightly news on another, and they had adjusted the image to remove the logo of the competitor. And they didn't say that this image was doctored from the game. And hey, we paid good money to have that advertisement there. But this is a really nice application of base expansions. We've talked about different bases. We've talked about base 10, base 2. Here's a nice application. We can use this to embed images inside images. This is called steganography. Okay, so any questions about this? Okay, so now we're at the point where we can set up what we're going to be doing for Hensel's lemma. So the equation that we're going to be looking at is f of x is x cubed minus 15x squared plus 11x plus 2 equals 0. So we want to solve this. All right, so I'll try to make sure this is. So the first is solve mod 2. So when we look at this equation mod 2, what do we get? So when we look at it mod 2, all we care about is even or odd. I can't, as soon as you die, it's Kayla's turn. Okay? When we look at x cubed, mod 2 x cubed is just? It's just x cubed. What about minus 15x squared? What is that? Minus x squared, or just plus x squared even. What about 11x? What is that? X. And what about 2? Just 0. And actually, if you wanted to, if you're looking at things mod 2, what is x squared mod 2? It's just x. And x cubed is also just x. So really, this is the equation 3x equals 0. Well, what's 3x when we look at it mod 2? X. So we get the initial equation. This has a solution mod 2. The solution is x equals 0. So because there's a solution mod 2, there's a chance that there could be an integer solution to this. And now we're going to look at the equation mod 2 squared. So mod 2, Cam, if you died, give it to Kayla. Okay? Just be quiet. So now let's try to solve mod 2 squared. What does x cubed look like mod 2 squared? Let's just keep it simple right now. It's just x cubed. What about minus 15x squared? It's just plus 1. 16 would be 0, right, because it's 4 times 4. So if I add 16x squared, I'm not changing anything. So this is x cubed plus x squared. What about 11x? What does that look like? That would just be 3x plus 2 equals 0. And now I want to try solutions that are 0, 1, 2, or 3. But we know when we look at it mod 2 that the solution was a 0. No. Yeah, okay, we have 3 minutes left, so no. So when we look at it mod 2, we know the solution is 0. So now let's guess x is equal to 0 plus some multiple, I guess I'll call it b, of 2. Okay? And now when we plug in here, what would x squared be? That would be 4b. And what would x cubed be? It would just be 8b. I'm sorry, 4b squared, 8b cubed. I know b is either 0 or 1, so b squared is the same as b, but I won't worry about that. When I look at things mod 4, what do you know about 4 squared? It's 0. And what about 8b cubed? It's also 0. So when I look at this mod 4, I don't really have to worry about the x cubed term. I don't have to worry about the x squared term, because I know when I looked at it mod 2, my solution was 0. So I'm guessing 0 plus 2b. And so now this will go away. This will go away. 3x becomes 3 times 0 plus 2b plus 2 equals 0. So I get 6b plus 2 equals 0. What is 6b the same as? 2b. Plus 2 equals 0. So what does b equal? So I want to solve this mod 4. This is always mod 4. So what's the only solution that works for b mod 4? So b is 1 or 3. But actually, when we think about it, remember we're writing it as 0 plus b times 2. So b can only be 0 or 1. Right? So the only possibility is b is 1. And so now we get our next solution. We went mod 2, we had 0. Mod 4, we have 0 plus 1 times 2. Mod 8, we would like 0 plus 1 times 2 plus something times 2 squared. And the idea is that we want to continue this process, and we want to keep generating the terms, just like we did the series expansions for the differential equations. So the natural questions to ask is, will we always be able to generate the next term? If there's an integer solution, yes. And the next question is, if we can always generate terms, does that mean there must be a solution to the original problem? And sadly, that's a no. So on Wednesday, we will then finish Hensel's lemma. We'll state what it is rigorously and show how you actually make this process work. But I want to give you some sense of where the p-adics come from and why we care about stuff like this. Okay.